Hey everybody, thanks for coming along to my talk. So I will be talking about resumable parser combinators, and you're probably wondering already, what is this and what is it useful for? So resumable parser combinators, as the name suggests, are parser combinators where the parsing can be suspended and resumed. The question naturally arises, why do you want to do this? And the answer is, at least the answer I'm going to give, is for embedded domain-specific languages. So in this talk, I'm going to be showing how we can implement these resumable parser combinators. It turns out to be reasonably involved. And then I also want to give you some reasonable lessons that can apply to other projects. I think it's unlikely you're going to implement this yourself in your own project, but I think a lot of the design techniques, the way I built this library, can be used to whatever project you may be working on. Before we get into that, though, let's talk a little bit about notation. So here on the screen is a picture of some musical notation written by a guy called Johann Sebastian Bach. And what's interesting about this is it's very dense, very domain-specific notation. It can be used by a musician to communicate to another musician how to reconstruct a piece of music. So in a sense, you can think of it as a programming language, a very custom, specific programming language that one musician can use to program another musician to recreate some music. So very handy. Notation is not restricted just to music. Here's another bit of notation. It's the PDF for the Gaussian or normal distribution. And again, it's very domain specific. The meaning of all these symbols is known to mathematicians and possibly not widely known outside of that. In fact, I would say definitely not widely known outside mathematics. But having this very terse domain specific notation is very useful for mathematicians or statisticians to communicate with one another. Here's another bit of notation, this time computer code. This is the mini notation in a Haskell library called title cycles. And within the string here, that's the actual mini notation, we have a description for a rhythm. BD stands for bass drum, this is snare drum, this is hi-hat. So this is, again, a very compact notation for representing a domain-specific context, in this case, a repeating pattern, rhythmic pattern. And we see that terseness again. And in this case, we're communicating with the computer. And here's another final example of notation. And this will hopefully be familiar to every one of you watching this. And this is, of course, Scala Code. So what we're seeing here is actually a little bit of code from the project I'm talking about. And we can see that Scala is a particular notation we can use to communicate with other programmers about how we might implement something, and also how we can communicate with the computer or the compiler. So notation is ubiquitous. Oops. It's really important, but in a lot of programming, we don't give much thought to it. Notation is seen as sort of an afterthought, not the main thing. And while I think that's true to a certain extent, I think there's a lot we can do with notation, particularly if we expand the concept of notation away from just text to, say, graphical interfaces. And it's really something we can explore a little bit more than we have. So what I'm going to look at is using string interpolation to provide custom notations and how we can use that to create domain-specific languages. And specifically, we're going to be looking at embedded domain-specific languages. And by embedded, what I mean is a DSL, domain-specific language, that lives within some other host programming language. So it's not like a little DSL which is written in its own file and has its own interpreter that runs with it. It's a DSL that's written inside another programming language. And this brings several advantages. One of the advantages, we can produce values that are used by the host. So when our program runs, our DSL runs, we can produce something that's used by the rest of our program. Another thing we can do is we can accept values into our DSL from the host. So the sharing goes both ways. And that's really handy because it allows us to compose programs together using the facilities provided by our host language. So you don't need to re-implement module systems or packages and namespaces, scoping, all this kind of stuff. We can get that for free. And we can also interoperate with the host. So we don't need to rebuild our standard library or whatever, or work on our runtime, we can get that all from the host language. So embedded DSLs are, in my opinion, really powerful. Then you get the question of notation, though. How do you implement the notation that you may have in mind? Scala is pretty flexible in these regards. We can do a lot with symbols and things like that. And some of the early Scala libraries went down this road. But there are still limits to what we can do. So to be more flexible, we can look at string interpolation. So here I want to talk about the details of Scala string interpolation, because I think it's quite reasonable if you're not familiar with all of those little details. So let's look at a string, say this string, and break down the individual parts of it. So the idea here is this would be some custom notation, use our own custom hieroglyphs, and we actually have real hieroglyphs here. And then we have some interpolated value, which is interoperating with the host. So let's go from the beginning. So first, this little name in front of the string, eval, you probably used S in your Scala code already. This chooses the custom interpreter. So this is the hook by which we can put our own processing into this string. The next bit is this arbitrary notation. Because it's a string, we can put a lot of different things in here. We can play with the full Unicode character set if we want. Admittedly, there are things we can't put in strings, but I think we still have a lot more flexibility than the basic Scala syntax. So a string allows us to put reasonably arbitrary notation. And then we have an interpolated value. And this allows us to inject those values from the host into our string or into our DSL. So the custom interpreter, the eval, is producing the values that the host can use. And the interpolation is how the values go from the host into our DSL. And the final thing you need to know about string interpolation is that it doesn't have to produce a string. It can produce a value of whatever type we like, not just a string. That's really important. So taking all this together, we can say that string interpolation allows for embedded DSLs with custom notation. So that should be fairly nice for doing the kind of things I'm interested in talking about here. But there's a problem, which is how do we parse it? Now, I need to emphasize this is not regular parsing. Okay, it's very different, and let's see why. So the first thing is that you can suspend the parsing with interpolation. So we saw earlier have an interpolated value, and that's saying stop parsing, and here comes the value. And remember, these interpolated values are not necessarily strings. They're values that we're sharing from the host with the DSL. So they could be any other type we're interested in. What this means is that you can't just take a normal parsing algorithm, because you don't necessarily want to turn these values into strings. There might be functions, for example, that don't have any string representation. So standard parsing, you can't just call toString and then just use a standard parser on that. When you've handled this value, though, you can resume parsing with more string input. So this problem is a little bit more complicated than your basic parsing. And the real challenge is handling this interpolation where you get a non-string value injected. You need to suspend parsing, handle this non-string value, and then resume parsing. And that's the problem I'm tackling in this talk. So let's go into designing resumable parsers. How does this work? So parsing is easy by itself for some definition of easy. But what I mean by that really is we have a pretty good technology, parser combinators, which are fairly easy to use. So here's an example of how you could use parser combinators to write a parser for a very simple arithmetic expression, like 1 + 2 or 3 take 4. We define here a parser for operators, which is one of plus or minus. We define here a parser for a number, which is characters while they're a digit. And then an expression is a number, followed by an operator, followed by a number. Now, I think this parser is fairly easy to read. I hope you agree with that. And it gives you an example of the power of parser combinators. Certainly, this parser is a bit limited. For example, we're not looking for white space in between the number and the operator. And in a real parser, we want to add in these features. That'll make the example a little bit too big, but hopefully this gives you the idea of what I'm talking about if you haven't used parser combinators before. So as well as being easy to use, parser combinators are also fairly easy to implement. They use what is by now fairly standard technology in the world of functional programming. And that is you define an API. And in my case, I basically copied the API from Cat's parse, added a few things that were specific to what I was doing and didn't implement some of the features that I didn't need. But basically, it's Cat's parse. Then I reified the combinators as enum cases. So I'm using a mixture of Scala 3 terminology, that's enum. In Scala 2, that's a sealed trait extended by a bunch of case classes. And by reify, what I'm meaning in the abstract is to take something abstract and make it concrete. And concretely, in this example, what I'm meaning is to take a method call, a call to one of these combinators, such as one of here that we saw earlier, or Charles while, and turn that into a data structure. So turn it into a case class in Scala 2 or an enum case in Scala 3. So that's the concrete part. So what this is doing is when you construct a parser, you're building up a data structure that represents the actions you want that parser to carry out. And then when you actually call that parser on a string, tell it to parse a string, you have what you can think of as an interpreter that walks down this structure you've created and carries out those instructions that are represented by the data. So there's some fancy names for this. Enum cases, algebraic data types, walking over the tree, structural recursion, pattern matching is a huge implementation technique. And these techniques are reasonably well known. I'm not going to say everyone knows them, and you shouldn't feel bad if you don't, but they're fairly widely known in the community. So if you know the techniques and understand parser combinators, you can implement parser combinators in, say, an afternoon. It's not particularly difficult. And we have this kind of structure here. So we have the type parser, which is just this basic parser combinator library. We have the method parse, where we give it an input. That's our interpreter. And we get back some result of type A. I'm going to talk more about the result type later. And this type A is the type of the parsed value. So we're showing here that a parser doesn't return a string. It can return some more structured data. So in the case of the expressions we are parsing, the example, we might want to actually produce some data structure that represents the expression, or even evaluate the expression to create a number. So we're not just dealing with strings here. Okay, so that's our basic building block, basic parser combinators. Now we get into what's kind of the meat of the talk, really, which is controlling this suspension, injection, and resumption. And let's talk about what's going on here. So I want to use the example of parsing Markdown, both because that's what I actually used the library for, and also because I think it's probably familiar for a lot of you, and it's a fairly simple format. So specifically, let's look at parsing this heading. Heading consists of the following components. We have these hashes which tell us the level of the heading. In this case, 3 hashes means a third level heading, H3. Then we have a space, 1 or more spaces, and then we have the text of the heading. And what we want to think about is, what does it mean if the parsing is suspended at particular points in this grammar? What should we do? Do we allow suspension, interruption? Do we not allow it? If we do allow suspension, what do we do when we resume parsing? And remembering that when we injected values, when we're suspending, we're injecting values which are not strings. They are parsed content already. In this case, they're going to be like our representation of a Markdown document. Right, so let's go. When can we suspend parsing? So imagine here that we're looking at these hash marks. We've seen these 2 hash marks, and this is how far we got in parsing. Could we do interpolation at this point? The answer is no. And the reason is, remember that interpolation is a parsed document. You can't put a document in here until you've determined what the level of the heading is. And it's not valid to just have a document fragment immediately after the hashes. We need to have that separating space. So we call this committing in the library. We must commit to finishing this parser. And if we're interrupted, if it's attempted suspension, then that's a parsing error. That's the first case we need. Now, what if we've seen one or more spaces? In this case, you can have an interpolated value, because the interpolated value is a document, remember, and that document will just be the content that makes up the heading, and that's mostly valid in Markdown. Now, there is the simple decision of what we do when we resume parsing. And what we don't do is go looking back for more spaces. Once we've seen one space or more and then got some content, even if that content is interpolated, we should advance to the next parser. And the next parser is going to be parsing any text that remains up until the end of the line, which is a text making up the name of, text making up the content of the heading. The third case is if we get suspended whilst parsing the heading text. And the action we take here is we just resume the parsing with the same parser. So we insert this document fragment as part of our heading, and then we go back to parsing document heading until we get to the end of the line. So this makes up the control API, the three different cases. We commit to a particular parser, and that means we cannot be suspended. We advance to the next parser if we're suspended, or we resume this parser when we come back from suspension. So those are the three cases that we have to handle. And implementing this API lifts us from a type which is our parser type to what I'm calling suspendable. An interesting thing to notice here is we have an additional type parameter. And this is the type of the intermediate values that we are accumulating, and is often the same as the output value type, but not always, because sometimes that type that we're working with is before we've processed our input, before we've turned it into some more structured type. So it could be, for example, string or something else. So keeping these two types around gives us a bit of flexibility that we need. By the way, feel free to use the comments channel if you have questions. It's very difficult for me to see how people are receiving this, whether I should go faster or slower. I'm happy to take directions from people in the comments. All right. Another piece we need is the result type from the parser. So if you remember when we looked at parser, our parser combinators, we had this result type. And this gives us information that we use to, sorry, got distracted by a notification on my phone. So it gives us information that we use for the control flow when we're doing this suspension and resumption. So there are four cases here. We get epsilon, which means we parse nothing. We get committed, which means we parse something and then failed. Get success, which means successfully parsed the input. And we get continue, which means we successfully parse all of the input and we'd be willing to keep on parsing if more input was made available. These first three cases come from cat's parse, which in turn takes them from a Haskell library I've forgotten the name of. And this continue one is unique to my implementation, and this is, as you can imagine, important for the semantics of suspending and resuming. It indicates that we're willing to resume this parser if that's what we're asked to do. All right, so this basic sketch of types is a sufficient framework to implement. Let's start down the road talking about implementation. So let's go and do that. So talk about the implementation techniques. So we need to talk about one more thing here, which is the parse method on suspendable. Remember, suspendable is a parser combinator that can be suspended and resumed. And parse is like the interpreter for it, and this produces a resumable. So a resumable is a result, but it's also a result that can possibly be resumed with more input. And it has the same types as before, S for the intermediate values and A for the output value type. And the API for resumable looks like this. We have a method to complete. Completing is saying, here's your final piece of input, parse it to the end as far as you can and don't suspend. We have a method called inject, which means add an already parsed, already computed intermediate value. So you see the type here is type S. And then we have resume parsing, giving some additional input, and possibly suspending again. Okay, so 3 things we can do. So Resumable is going to, Resumable represents a parser basically that we can continue, a result, and a parser that we maybe continue. And then we can either complete that with additional input, add parse values into the parsing stream, or resume and possibly suspend again with additional input. Now, a lot of the implementation here is standard. It's the same kind of reify interpreter pattern that I talked about in the basic parser combinators. But there is an additional wrinkle, which is how exactly do we use suspending? How do we write a parser that we can suspend during parsing? And how do we do the injection and resumption? And suspension is the most challenging bit here. So let's talk about continuation parsing style. So continuation parsing style, parsing being different from parsing, but I'll make sure I pronounce those correctly, is a program transformation that allows us to reify, one of my favorite words, the control flow. And if you remember, reification means making something abstract concrete. And in this case, it's making the control flow from abstract into something that's actually represented as a value in our program. And the way that works is that each method gains an additional parameter, and that parameter is a function, and that function represents what's happened next. So these functions are representing the control flow because they're representing this is the thing that should happen next. You can call this function and make it happen next. Okay. These functions go by the name of continuations. So CPS functions or methods don't return. They just call the continuation with the next value. And I'll give you an example here. So here we have some normal straight line code, sometimes called direct style. We have function 1, because that name resolve that A, we pass A to function 2, call the result B, and then the result of this whole thing is calling function 3 with A and B. And we're going to convert this into continuation parsing style. So remember, in continuation parsing style, each functional method gets an additional parameter, and that parameter is what you should call to do the next step. So the CPS code looks like this. So function 1, which had no parameters initially, takes an additional parameter, which is a function, and that function takes the value A and then does the next step. And the next step was to take A and call function 2. So we call function 2 with A, and now function 2 gets an additional parameter, and this is a function which takes B as a parameter and goes on and does its next step, which was calling function 3 with A and B. And that's what we do. And of course, we have the additional parameter here, which is a continuation, which accepts the value C. I've called the result of function 3, and then we just return C. So this is continuation parsing style, the transform from direct style to continuation parsing style. Hopefully it gives you an idea of how to do this. So this is a very mechanical procedure, and you could write code to do it, or more often you end up doing it by hand. So the continuations here explicitly represent the control flow. These functions are a reification, if you like, of the control flow. And what this means is if you want to pause something, you just need to save the continuation somewhere. Stash that function in some kind of variable, say. And then when you want to resume computation, you can just call that function that you stashed away, and things will get back and proceed. So this is the technology which gives us the ability to suspend and resume a computation. Very cool. So what this means is the interpreter, the parse function for suspendable, is written in continuation parsing style. And if we encounter the end of the input, then we may suspend the current parser. We use the control API to determine what we do on the end of input, whether we advance, commit, or resume. And then we have that resumable type, which is storing the suspended value so that we can resume it later if additional input becomes available. All right. So I think it's useful to see some CPS code in the interpreter in this parse method. And so I've got a little fraction on here. And this is inside a little helper method, which is called loop, which is inside parse. And you see we have an input, which is a string, an offset in that string that we should start parsing from, and then the continuation, what we're at, the sort of thing we should do next. And this case here is the or else case. What or else means is you should parse with left. If it succeeds, then the whole thing succeeds. If it doesn't succeed, then you try the right parser instead. So the way it works is we call the loop method on left with the same input in the offset, and the continuation here, which accepts the result of the parsing, is going to look at this result. If it's an epsilon failure, meaning we parse nothing, then we go onto the right loop, go onto right, parsing that with the continuation. And in all other cases, we just call the continuation with this result, and the continuation that we're calling, which is here, may do some other handling with that, for example, suspending or resuming, and so on. So let's see another case which is going to actually show this suspending, resuming, the control API at work. So this is a case where we're handling a resume. So what this means is if this parser is willing to accept more input, which it signals with continue, when we resume, we should resume parsing this parser. So the case works pretty much as I've just described. We try to parse the input from the offset. This is a parser, not a suspendable. And the result success, well, then we continue success. If we get continue, which means I read all of the input, I'm happy with it, and I'm willing to read more, we then suspend, and we store the source that we parsed. It's probably this value A here, a semi-group, which we've captured. This is probably a typo, probably should be S. This semi-group, which allows us to combine results, we'll see it later, and the continuation, which will allow us to continue parsing. And then on the other cases, committed epsilon, we just parse it to the continuation to hand as before. Okay, so that's how it works, the continuation parsing style, and then the control API to take the appropriate action. I hope it seems reasonably simple. It is fairly involved code, I must admit. Other thing we should look at then is how this resumable type works. Remember, the resumable is storing the continuation that we're going to resume. And resumable basically consists of two cases. It's an algebraic data type and enum. We have the case where we're finished and we have a result, or the case where we've suspended and we can be resumed. So when suspended, we store the parser that we suspended at. We store the partial result, the intermediate value that we parsed, which is of type S, not the final result type A. Semi-group, which we on type S, and a continuation, which accepts values of type S and will return the value of type A. And then let's look at some of the methods on resumable. So I think inject is an interesting one. And this is where we have a parsed value coming into the parsing stream. And what we do here is, if we are suspended, we combine this value with the intermediate value we had stored before. If we're finished, well, we can't do anything with it, so we just ignore it. So that's how we inject values, just by using this semi-group. And another bit that's interesting is resuming parsing. And completion, which is parse but don't resume, is very similar, so I haven't shown it. So what resumption means, if we're finished, well, we're finished, we can't resume. But if we're suspended, then we take the parser, parse the input we've been given, starting at offset 0, and then we look at the output, and if it's a suspended value, then we combine this partial result with the partial result we just generated here, and keep that suspension around. So that's broadly how it works. So to recap, we have the continuation parsing style in the parser in suspendable, which allows us to write the program in such a way that we can capture the control flow, stash it away in a data type, and resume it. And that data type we stash it away in is resumable here. And that stores the parser we could resume, an intermediate value, and some other little bits and pieces we need, machinery. So that's essentially how you implement resumable parser combinators. I think the next question to come along is, does it work? And the answer is yes, it does. And you can have a look at the code here. So it's just a little project at the moment. One note about this code, it does work. There's an issue in Scala 3, an exhaustivity checking bug, which means that the code doesn't compile with compiler warnings turned into errors, which is the usual way I program. I don't have a pressing need to release this code at the moment, so I haven't turned off the compiler warnings and compiled the code and released it. I'm hoping this issue will be fixed soon, and then I can just migrate to Scala 3.1. Whatever, and go from there. If anybody would like me to release it, just let me know, and we kind of release from what's there at the moment. I also have a project that uses this. It's original motivation. And what this does is provides a markdown string interpolator. And I think a reasonable question is, why would you want a markdown string interpolator? That seems a pretty weird thing. But it's actually, in my mind, a great example of the power of notation. Writing documentation in Markdown is pretty easy because Markdown gives you very terse syntax, very compact syntax, just like musical notation, for writing most of the things that are in a document. The problem with Markdown, the problem I've found in the various uses I've used it, and I've written a lot of Markdown, I've written several books in it, lots of blog posts, is I always run into problems with the extensibility of Markdown. So, for example, in the books, we wanted to have solutions as little drop-downs or little links, depending on the output format, and we had to hack that into the Markdown processing. And in the documentation that I'm working on, I really want to have rich documentation. So I work on a graphics library called Doodle. I want to actually embed images in the documentation, and I want to make the images hooked up to little controls so you can adjust things like the colors and size and so on and see how they change. And you can't do this in Markdown, and I could add arbitrary extensions to it, but I'd really rather not add arbitrary extensions. I've gone down that route and it just runs into a problem. What I'd like to do is use a general purpose programming language, i.e. Scala, to compute values, i.e. document elements, rich document elements, like maybe little JavaScript components that I then inject into my Markdown. And that's exactly the problem I've described earlier. I can write my Markdown as strings, which get parsed into some document representation. And I then can inject these values I construct outside of the Markdown, which have these rich interactive components. So that's my motivation here. Still in work in progress, but it's pretty cool. All right. Now, as I said at the beginning, it's unlikely you are going to actually implement resumable parser combinators yourself. Although if you did, now you know how to, perhaps. But there are some reusable lessons for what I've done that I think apply to just about any project. So let's first talk about Dotty. Actually, let's not talk about Dotty because it doesn't exist anymore. Let's talk about Scala 3. And my experience is generally Scala 3 is very nice. So these projects are written in Scala 3, as you've probably seen from the examples of code. The basic things, like your algebraic data types and so forth, are much nicer in Scala 3. The terse syntax is really nice, just less typing, and a lot of the rough edges have been smoothed off. However, there are new rough edges, which is not all of the new stuff working. So I gave the example of this exhaustivity checking bug, which is blocking the release of the resumable parser combinators. There are a few other issues in the actual code base. I wanted to abstract over this control API for reasons that are not particularly important. And I wanted to try using a contextual function for that, but I couldn't get it to compile. And I'm fairly sure that was a compiler bug, and it might have been fixed now. So not all of the new toys work, but for your general day-to-day programming, I don't think you'll be needing a lot of these toys. Pretty much everything you do in Scala 2 works in Scala 3 and is better. So if I think you're moving, I generally think it's getting pretty good. You might hold off for a few more months, but I'm not adverse to jumping into Scala 3 at this point. It works very well for what it is. Having wider applicability to Scala 2 and Scala 3 are some of the programming strategies, as I call them, which I used here. So what I think of as programming strategies are repeatable processes that apply to programming. So programming is not just about sort of static knowledge, like what is a class. It's also about dynamic processes, the way we write code. And we can recognize when we're repeating these processes and formalize them. And that's what I'm trying to do to some extent. So one of these processes is this construction using interpreters. So all the code I've talked about is based around this interpreter model. It's a particular type of interpreter where we reify the combinators as algebraic data types. And we have to implement the interpreter as a structural recursion over this reified data structure. Or in more concrete terms, into the language features in Scala we use, the algebraic data types are your enums or your sealed traits and case classes, and your structural recursion is your pattern matching on that data structure. This idea of interpreters is core to functional programming. There are two reasons for it, and I think they're really related. In fact, you might just say there's one reason, and that's basically making code easier to understand, allowing us to reason about what the program is doing. So we see this in the IO monad, for example, like the cat's effect IO, where we have this rich language for describing what we do with concurrency and interruption and so forth. And we specify what we want the program to do as an IO monad, and then we go ahead and run it. And it's the same thing in the parser combinators. We specify what we want to do in terms of parsing and how we should handle suspending the parser, and then we provide some input and go ahead and run things. And the reason we do this is these descriptions of the program are much easier to understand what they're going to do. And particularly when we have side effects, this is how we hide side effects, by having this pure description of the program. And then when you actually come to run it, that's when you go and do all those dirty side effects that we still have to do in our program, but we sort of don't want to do them in the bulk of our program. So this interpreter pattern is core to functional programming. Now, there's a lot of discussion about interpreter pattern and ways to write them in the functional programming world. And on the left-hand side, I just have basically different terms for the approach I use. So I call it reified, which is essentially turning abstract things concretely, turning methods into data. It's contrasted with the church encoding, which is where you represent everything as functions. And in category theory land, this is sometimes known as initial versus a final encoding. And in other places, you'll find this called a deep versus a shallow embedding. So there's a rich set of ideas here and different trade-offs and different representations. And this is great because you can take one basic idea, which is I want to implement this interpreter with the following combinations and so forth, combinators and so on. And then you have this big design space that other people have explored, and you can find all these techniques and just apply them in a very mechanical way, which is great. One of the other things we saw was continuation parsing style, which is how we can capture the control flow of the program, suspend it, and resume it at arbitrary points. This is not something you need to do very often, but when you do need to do it, it's really handy. Some things you can do here are make things stack safe, because we don't have tail calls in Scala yet. Maybe we'll get them when Project Loom ships. So you might need to implement things in continuation parsing style and have what's called a trampoline to make them be stack safe, make their stack consumption not grow without bound. Another thing you can do here is you can implement all sorts of crazy control flow. I've implemented this suspending and resuming, which is reasonably different to how we normally do things. You can do all sorts of complicated things you want, like backtracking and so on. Can be very handy for multi-threaded type runtimes and so on. So it's a useful trick to have. then there are some bigger principles at play here. So one of these, I think this is really important in functional programming, is giving the programmer control over the semantics, making it really explicit in the program what the behavior of that program will be. One example of this is the control API, which is where we decide whether we're going to suspend, we decide when we suspend whether that's an error, we're going to resume that same parser, or we're going to advance to the next parser. And when I started implementing this, I was making a decision based on the particular combinator you'd chosen. And then that soon, I just couldn't work out what was happening, and I realized that was a mistake, and I needed to make that control flow explicit in the program so I could reason about it. Another place that we have this is by having different concepts with different types. So for example, we had the parser type, which is the basic parser combinator library. And then I had the suspendable type, which is a suspendable parser combinator. And they're different types. And that's important for understanding, again, because you can use the control API to go from a parser to suspendable, but you can't take a suspendable and then try to use that control API on again. That would lead to very odd semantics. And again, that's not something I initially started with. It's something I realized I had to do once I started writing the code, and I saw that implementing this control in a way that I could understand was going to be very hard if I merged these two concepts together. They really needed to be different concepts. So that's something I see a lot in functional programming. You try to make explicit what the program is doing, allow you to understand it, and something we don't see sort of the imperative programming so much, where it's just like whatever happens, happens. All right. Okay, already said that. So quickly, I just want to say that the Bach music notation, a prelude from something other, comes from Wikipedia as public domain. And thank you for listening. You've been an amazing audience. If you're interested in the code, those are the links again. And let me have your questions.
Hey, Noel, thank you so much.
Hello.
All right, let's jump into questions. In the Resumable API, the type S stayed the same when you resume a resumable. Isn't it possible that a new bit of input gives you more data, which better fits in a new intermediate type?
Right. So there are definitely limitations here by making, there's only one type parameter for S, which is, so basically whatever you inject has to fit under that same type, and it stays constant. You could make a more flexible system. I'm not sure. I think what you're specifically suggesting here would make the implementation quite complex. I think it becomes dependently typed in this case. I suppose you could do something with implicit evidence to specify those typing rules. So there's a trade-off here between what you express in the type system and the complexity of the implementation. And I went for something that was fairly simple and fairly tractable to work with, and that does exclude some cases, or at least loses some typing information in more complicated cases. An example might be, say, in Markdown, inside a heading, you can have only certain types of formatted text. You can't have a heading which also contains a list, I don't believe, or a table. So I lose that information just by having that single type to represent a document. You can make it more complicated, but then you have to implement it and make all the types line up. But yeah, good question.
All right, let's move on to the next question. Why are you capturing the semigroup for intermediate results instead of taking it implicitly? And can that lead to inconsistencies?
Right. Why am I capturing the semigroup? That's a good question. Do I need to capture it? Okay. I don't have a good answer for that. I'd need to look at the code and go over thinking. I think maybe I believe at some point that type wasn't known. And I'm not sure if the design changed and now the type is known, or if there actually is something in there so that the point where you inject the type is not known. That doesn't really make sense. So I think it might just be an artifact of change implementation not getting cleaned up. But yeah, that's a good question.
Very good question. Thank you for answering that. Just taking a quick look here, it looks like we don't have any more questions at the moment. So I'd like to thank you very much for sharing with us today, and I hope you get to enjoy the rest of the conference, and we'll see you at the panel discussion later today as well.
Yep. All right, great. Thanks a lot. Thanks, everyone.
Thank you. See you soon.
Bye.